Okay, so welcome to session 9, Graphs and Satisfaction, slightly more exciting session than the other ones. Okay, so the first talk is complete symmetry breaking constraints for the class of uniquely Hamiltonian graphs. Okay, and the speaker is Avraham. Okay, please play the video.
Hi everyone, my name is Itzhakov, and in this talk I'm going to show you a significant class of graphs for which complete symmetry breaking constraints of polynomial size exist, and we will see why it is interesting. So our work on symmetry breaking is addressed for graph search problems. In these problems, the goal is to find a simple graph which satisfies certain structural properties. One of the most famous graph search problems is the Ramsey problem, where for ST and N asks to find an Euler-n graph that does not contain a clique of size S nor an independent set of size T. And here the depicted graph is a solution for the parameter 3, 3, and 5. For graph search problems, every vertex permutation is a symmetry. Isomorphic graphs, which by definition have the same structure and only differ in the names of the vertices, are symmetric representations. Here we have two graphs which are isomorphic. The left graph is the graph that I showed you in the previous slide, and the right graph can be obtained from the left graph via the permutation which swaps the vertex 2 and vertex 3 and vertex 4 with vertex 5. So these symmetries, together with enormous search space, make graph search problems highly challenging, and symmetry breaking is crucial to solve them. The way we solve graph search problems is using a constraint-based approach. We model graph search problems as constraint satisfaction problem. The unknown graph is represented using a set of Boolean variables which indicate the adjacency matrix of the solution, and the desired structural properties are modeled as constraints over these variables. Additionally, we add symmetry breaking constraints to deal with symmetries in the search space. Unfortunately, there is no compact way to express a complete symmetry breaking constraint for graph search problems. And what is the meaning of complete symmetry breaking constraint? A symmetry breaking constraint is said to be complete if it is satisfied by exactly one member of each isomorphism class. And all known techniques to define complete symmetry breaking constraints are based on predicates of exponential size. So the problem that we are dealing with is to design a complete and compact symmetry breaking constraint for graph search problems. And this turns out to be a really hard problem. In computer science, when we deal with hard problems, we typically try one of the following approaches. We may apply a brute force approach, we may find an approximation algorithm, an efficient approximation algorithm, or we identify special cases where we can solve the problem in an efficient way. And this approach is the one that we are concerned in this paper. We identify a significant class of graphs for which we can find polynomial-sized symmetry breaking constraints which are complete. So what does that mean? Being complete for a specific class, we need to modify the definition for complete symmetry breaking constraint. So a symmetry breaking constraint is complete for a specific class C, a graph class, if it is satisfied by exactly one member of each isomorphism class of graphs belonging to C. We only care about the isomorphism classes of graphs that belong to the class C and not all the isomorphism classes. And this is the difference between this definition and the general case. And the particular class we are dealing with in this paper is the class of uniquely Hamiltonian graphs. So these are graphs which contain exactly one Hamiltonian cycle. And the research community has put a particular focus on uniquely Hamiltonian graphs of minimum degree 3, or UH3 graphs for short. And these two graphs here that are depicted are both uniquely Hamiltonian graphs, and their Hamiltonian cycles are colored in red. They are also UH3 graphs. The main contribution of this paper is a complete symmetry breaking constraint that is of polynomial size for uniquely Hamiltonian graphs. The basic idea of the constraint is as follows. When we fix the Hamiltonian cycle in the graph, and then we break the rest of the symmetries using a polynomial size constraint. So formally, the symmetry breaking constraint is defined as follows. It has two parts. The first part fixes the cycle graph in the unknown graph G. And the second part requires that the graph G is smaller, lexicographically smaller than its isomorphic representations, where the permutations are taken from the automorphism group of Cn. And it is important to note about the automorphism group that it has only 2n permutations. So to express the constraint here that breaks the rest of the symmetries, we can do it using a polynomial sized constraint, or actually using linear number of flex constraints. So here we have an example of the constraint SB of UH, of the symmetry breaking constraint. The first part, which fixes the cycle graph, is represented using the clause here. This clause ensures that the edges of the cycle graph will be present in the graph. The second part of the constraint is expressed using 2n lex constraints, or in this case, using 10 lex constraints. And the first one is erased because it corresponds to the identity permutation, so it is always true. So now we move on to the applications. So first we will look at the application of generating all uniquely Hamiltonian graphs modulo graph isomorphism. So any generation algorithm which only generates non-isomorphic solutions, non-isomorphic uniquely Hamiltonian graphs, must deal with two issues. First, it must restrict the process to the graphs from that class, and it should eliminate symmetries among the generated graphs. The state-of-the-art generation algorithm is a dedicated algorithm, which for our purposes only important to know that it uses NOTI to eliminate symmetries. NOTI is really efficient, but it is potentially exponential in the worst case. Our approach, in contrast, is a constraint generate approach using a general purpose constraint solver. So let's move from theory to practice. Our constraint model has two parts. The first part ensures that the graph G that we search for is uniquely Hamiltonian, and the second part is the symmetry breaking constraint that I showed you in the previous slides. So we implemented this the first constraint using a propagator, a custom propagator. So to ensure the uniqueness of the Hamiltonian cycle, we implemented a propagator which works as follows. The propagator is triggered whenever a graph variable Gij is assigned true. In other words, whenever an edge Ij is added to the graph. The propagator then iterates on over every Hamiltonian path in the graphs which start with the edge Ij, and ensures that this Hamiltonian path cannot be closed to a Hamiltonian cycle. For example, here we have a partial assignment. The edges can be seen in the depicted graph here, and let's see what the propagator will do when an edge will be added to the graph. So assume now that the edge 2,5 is added to the graph, and now the propagator will try to find Hamiltonian paths which starts with 2,5, and for each of which, to ensure that it cannot be close to a cycle, so the propagator finds one Hamiltonian cycle. And for this Hamiltonian cycle, to ensure that it is not, for this Hamiltonian path, to ensure that it is not, cannot be close to a Hamiltonian cycle, the propagator forbids the edge 2,4, or in other words, it sets the variable G24 to false, and the propagator continues and finds more Hamiltonian paths, and for each of which it forbids the corresponding edge, so that these Hamiltonian paths cannot be closed to a cycle. So we implemented this constraint model on the top of Choco4 solver, and this table details the computation of uniquely Hamiltonian graphs, modular graph isomorphism. The first column indicates the size of the graphs. The second column specifies the number of uniquely Hamiltonian graphs. The third column is the total solving time was required to generate these graphs with our approach. And the fourth column has detailed statistics about the propagator that we just presented. And I will come back to these stats later. So let's look on a specific case where when the size of the graph is 13. So to generate the 9.7 billion solutions, our implementation, it takes for our implementation about 2.5 days. And now we can move on again to the propagator stats. So the propagator statistics indicates how many times the propagator was invoked, and also the total number of Hamiltonian paths that were encountered during all executions together. And we can see here that the number of Hamiltonian paths that were encountered is not too big. And this was something that we were worried about because the propagator iterates on every Hamiltonian path which starts with a specific edge, and it is not a concern as we can see here in the statistics. So now we move on to another application, which is about an unresolved question regarding uniquely Hamiltonian graphs of minimum degree 3 with specified curve. So there are several papers about this topic, and we chose two unresolved questions to tackle. So the question were, first, to determine the smallest order for which uniquely Hamiltonian graphs of minimum degree 3 with graphs 3 and 4 exist. And second, we would like to find all such smallest graphs. So using our approach, we were able to find the solutions for this problem. And these new results have been made possible using our approach, and specifically due to the complete symmetry breaking constraint of polynomial size. So if you remember these two graphs here that I showed you earlier, these are new graphs that were previously unknown, and we found them with our implementation in order to answer some of the questions earlier. So in conclusion, there is no known complete symmetry breaking constraint of polynomial size for graph search problems. Identifying such classes is important from both theoretical and practical points of view. And this paper takes a step in this direction. It shows a complete and polynomial sized symmetry breaking constraint for uniquely Hamiltonian graphs. Thank you for your attention.
Okay, any questions? Yes, Peter, you have a question?
Yeah. So I'm wondering, it looked like, Avi, that you always disallowed the last edge. If some of the other edges weren't necessarily in the graph when you were searching for Hamiltonian paths, why is it correct to disallow the last edge? Maybe you could disallow an edge in the middle and that would remove that Hamiltonian path.
Peter, if I understood your question correctly, then you ask whether more edges can be erased whenever the propagator is triggered, or can you?
Or the question was, why only the last edge is erased? Why couldn't I? Let's say I take the new edge, I take an unknown edge, I take a known edge, and then the last edge is another unknown edge, and that gives me a cycle, assume. Then in my mind, removing either of those two unknown edges would remove the possibility of that cycle, but you only seem to remove the last one.
Right. So first of all, we chose we look every time only on the last edge because it is sound, because every Hamiltonian cycle that can be generated, right, must involve the last edge if our propagator is correct. So we only care about the edges, the last edge that is added to the graph, right?
Is that because it's incident with the edge you've just added now? Is that why?
Yeah.
Okay.
So
Any other questions? Margin?
Hi. So maybe the obvious question here is: so how likely is it, or do you see any hope for a that the Ramsey property, so for given S and T, can be such a special property that, or special class for which you can have perfect symmetry breaking?
Yeah. So this paper takes a first step in this direction. I believe that there are more classes that we can find complete symmetry breaking constraints of polynomial size for them. And this paper also allows us to understand symmetry, let's say, to understand better the concept of symmetry in graphs, also for other classes, because the idea of taking a substructure and using the automorphisms of the structure to break symmetries is something that is new. So I believe that we can use such techniques to break symmetries for other classes as well.
Thank you. It's very exciting work.
Okay, and Jules?
Yes, in your first experiment, you report the number of isomorphic free graphs. Are you more interested? Do you want all of them, or are you more interested in knowing how many there are?
In our implementation, we actually can generate them, but for in our experiment, we only care about their number. But when we report the number, actually in our algorithm, in every time we found a solution, we have the graph itself. It's not a counting algorithm; it's actually a generation algorithm. Right,
but in the end, is it sufficient to know how many there are, or?
Excuse me, can you repeat?
But are you in the end, are you more interested in knowing what's important here, how many there are, or that you can generate them?
Right. So for the first experiment, I'm interested in how many graphs are there, because it is it only cares about generating all uniquely Hamiltonian graphs, but actually the interesting questions regarding uniquely Hamiltonian graphs are for very specific cases. So in these cases, as for example, the unresolved questions that we solved in this paper regarding uniquely Hamiltonian graphs of minimum degree 3, in these cases, we are actually interested in the graphs themselves and not only counting them.
Okay, thank you.
Okay, I guess hang on, now we for time because we are totally off schedule.